here we are with our last video of summarizing data with descriptive statistics. By the way, that's Belize. That's where I spent my vacation last year. Yeah, I travel a lot. Anyway, let's talk about something that you probably use in your daily life, even if you don't really think about it, and that is measures of variability or measures of dispersion. The average person in my family is 5'4". We're a short family. And that would be the mean. If I asked you, what's the height of the average person in your family? You could probably give me a number. And if I said, give or take what? Like, give or take 2 inches. Like I said, we're mostly pretty short. The range is 7 inches. I'm the shortest person. I'm 5'1". Rhonda's the tallest person. She's 5'8". We're a pretty short family. So if you can say something like, oh, the average person in my family is about 5'8", give or take 4 inches, then you're using that concept of variability in the average, even if you didn't put it in those terms. Now, what is variability? Variability refers to how spread out a group of scores is. So if you look at these two distributions test scores in two different classrooms, you could see that this one on the right is more spread out than the one on the left. It's obvious that they're different. Now, when we're summarizing continuous variables, in addition to the mean and the median and the mode, which we talked about last time, we also use measures of dispersion, the range, variance, the standard deviation, the interquartile range, and somewhat less often the semi-interquartile range. The range is simply the highest score minus the lowest score. So if you had all of these scores together right here, 99, 45, so on, the lowest score is 23, and the highest score is 99. That makes your range 99 minus 23. Going back to our earlier example of test scores, on the left distribution, the lowest score is 5 and the highest score is 9, therefore the range is 4. However, the variability on the right is larger, as you can see. The lowest score is 4 and the highest score is 10, and this makes the range 6. And here I've got my data set of people who said how many people are like family to you, and the range is 87. The lowest score was 0, 6 people said there was nobody like family to them, which is kind of sad. And one person said 87. So 87 minus 0. A second measure of variability is interquartile range, which is the range that contains the middle 50% of the scores. The interquartile range is calculated by subtracting the 25th percentile, which would be up here at 3, because the person who has the 25th percentile score would fall in here. And 10, that's where the person with the 75th percentile score would fall. So 10 minus 3 is 7, and that's our interquartile range. Find the score that the 25th percentile it falls in, find the score the 75th percentile falls at, and subtract 1 from the other. So 10 minus 3, 7. With our test scores again, we have the left distribution, 8 minus 6. This would be the 75th percentile, 25th percentile. The interquartile range is 2. On the right distribution, the 25th percentile is 5, and the 75th is 9. Pretty basic, right? The semi-interquartile range is just the interquartile range divided by 2. To get the semi-interquartile range, like I said, take the interquartile range divided by 2. I had 10, 75th percentile, minus 3, which is 25th percentile. I divided by 2, my semi-interquartile range for my scores on how many people are like family to you was 3.5, 3.5. Now, You might notice that one reason that the interquartile range or the semi-interquartile range could be more useful than the range is they're not affected by outliers. Without this one score, this very extreme score over here of 87, the range is 30. Instead, with that score, it's 87. But the interquartile range and semi-interquartile range don't change at all. If you had a small sample, dropping one score might change the 25th percentile or 75th percentile a little bit. But the point is, one score can have a huge impact on the range if it's an outlier, and not so much on the other two measures. Variance measures how close the scores in the distribution are to the middle of the distribution. And very specifically, it is the average squared difference of each score from the mean. And you'll see that in formula in 1 second. Now, this is the formula for the variance of the population. You won't use that very often because you don't often have everybody in the entire population. This is the score, so each individual person's score minus mu, which is the population mean. Each score minus the population mean squared, sum those up, divide by n, which is the total number of people in the population. Most often, this is what you're going to get. Very seldom do you have everybody in the population. You're going to have the same thing for each score. You subtract from that score the mean. This is your sample mean. Square it, divide it by n minus 1. Random fact you may want to know, when you have a population value, we use Greek letters like mu. And when you have a sample value, we use Roman letters like a regular M. Actually, though, Greek letters are also used for a lot of other things in formula. And I remember when I was in graduate school, and I really love statistics, but like everybody, I would sometimes get at points in my statistics courses where it was not so obvious. And I remember telling my husband, you know, people say it's all Greek to me. They write this stuff in freaking Greek, Ron. Anyway, yes, population values are shown with Greek letter, sample values shown with Roman letter, and we don't often get the population values. So that's the bottom one, that's the formula you're going to be using. Let's look at an example here. If you subtracted every score from the mean and added those up, that would be a reasonable thing you might ask. Why bother squaring them? Why don't we just take all the deviations from the mean and add them up? Because it's going to cancel out to 0 every single time. So that's not going to work. Instead, what we do is we square them because squares are all going to be positive. If you just added them all up, the negative differences from the mean, the positive differences would cancel out. And so the sum of the differences from the mean are 0. Some of the squared differences in the mean are not going to be 0. In this case, as you can see, our mean was 7. So 9 minus 7 is 2. Square that, you get 4. Down here, this person's score is 7. So 7 minus 7 is 0. Square that, you still get 0. This person's score is 6. 6 minus 7 is negative 1. Square that, you get 1, and so on. Here's another example. We're going to take these 4 scores, and we take all of them out, add them up, get 12, divide by 4, and that's 3. So this is our mean. To get the variance, we subtract the mean from each of those scores. 1 minus 3 squared, 2 minus 3 squared, and 4 minus 3 squared, 5 minus 3 squared, and divide that by 4 minus 1, which is 3. And that gives us 10 divided by 3, and our variance is then 3.333. As I said, we're almost always going to be using that second equation, the one where we're assuming that we have the variance of a sample, not the entire population. And in fact, when you compute the variance in Excel, it's going to tell you that it's estimating the variance based on a sample. And any statistical package that I can think of, the default, if you don't specify anything different, if you are doing a function for the variance or for the standard deviation, you're going to get the sample value, assuming that you have a sample, not a population. The standard deviation is simply the square root of the variance. So we took all of the differences from the mean and squared them, and now we're going to take the square root of that and get back to the same level of measurement that we had with the actual scores. In our example before, of the test scores, we had a variance of 1.5, so the standard deviation of that is 1.225. That is your standard deviation. Think about this. Because deviations from the mean are squared, a few extreme outliers can have a major effect on the standard deviation and the variance. If you had a small sample, dropping one score might change the 25th or the 75th percentile a little bit. But having one score that's an outlier when you're squaring it can change the variance or the standard deviation a lot. And here's my example. Looking at my example back with our how many people are like family to you, the variance with this outlier included was 158. Without that outlier, it was 48. The standard deviation with the outlier was 12.6. Without the outlier, taking out that one score out of 57 people, the standard deviation dropped from 12.6 to 6.9. And that's why we always want to look at outliers and analyze the data with and without them. Personally, if somebody's a really extreme outlier, and that one person would change your results dramatically, I kind of question if you ought to keep them in a study. When I'm doing research and I have an extreme outlier like that, I will drop them out, analyze the data with and without them, and report the results usually both ways. Now, the good news, if you were thinking, I'm never going to remember that formula, or I really don't want to find the difference from the mean for every single score and square it and add them up. The good news is no one computes standard deviation or variance by hand. Lots of calculators have statistical functions where you could type in all the numbers and click the standard deviation or variance button. In Excel, to get the variance, you could put equals VAR, type the reference for the first cell, like D2 colon the last cell, like D58, or you could just click and drag down so we have them all. But anyway, that's the variance function, standard deviation, STDEV, add same thing, click on your first cell that you want included, drag all the way down, and close parentheses. That's how you get your standard deviation. Just a reminder, standard deviation is the square root of the variance. The population standard deviation is this lowercase sigma. The sample standard deviation is S. Let's take a look at what the normal distribution looks like. In a normal distribution, 68% of the scores fall within one standard deviation of the mean, 95% fall within two standard deviations of the mean. The standard deviation is really relevant in statistics and probability, and the fact that 95% of a population will fall in a normal distribution within two standard deviations of the mean when data are randomly sampled, randomly generated is a really important thing in probability, really important thing in normal distributions, and that is coming up in a chapter in the future.